Now in our previous video, we discussed with only the real eigenvalue having eigenvalues one positive and one negative. Now today, and briefly, we'll be discussing about each and every categories and how does the phase portrait under every categories look like, we'll be discussing. So for this, let us first take the first example today. Let me consider an system matrix A having value -1, -2, 4 and 5. This is my first system matrix. Now, while solving the values, like if I choose lambda I minus A equal to 0, this is my concept. If I use this concept and find out the value of my eigenvalue using this system matrix, you will get two values, lambda I equals to 1 and 1 equals to 1 and lambda 2 equal to 3. And the same way, like Ax equal to lambda x, using the next concept, you'll be able to find out the first case when lambda 1 equals to 1, we'll get the state vector as 2 1, and in case of lambda 2 when equals to 3, we'll get the next state vector equal to 1 and 1. So we'll be having two equations. One will be y equal to half of x, another one y equal to x. This is my first case. So what do I see? As I already said, if I have an eigenvalue with both positive and both real, that means this particular system matrix's eigenvalue falls under this category, both positive. So when I have both positive eigenvalue and by obtaining the state vectors and the equation, I will be drawing a phase portrait by using phase plane and by using the phase variables. So you will be having respectively two curves. When I consider 0 0 as my equilibrium point of origin, so what do you see? As I already said, that when I have two positive eigenvalue means exponentially growing curve, that means neither of the two curves will be converging to 0, which means both of these curves having an arrow moving outside the origin. So in both cases, the arrows will be outside my origin. So then if I get this type of curve, how will my phase portrait look like? Your phase portrait will start like this. It will start following this arrow and then follow this arrow. Same way, these two are my phase portrait when I have two positive eigenvalue. Next category will be the second category when I consider a system matrix -3, 3, 0 and 2. Same thing, by using the concept of lambda I minus A equal to 0 and Ax equal to lambda x. Using these two concepts, you will be getting the values of eigenvalue 1, -3. For this, the eigenvector will be 1 and -3. And the second one, lambda 2 equal to -2. For this, eigenvector is 0 and 1. Now, what do we get here? We will be using these two eigenvector, and then by getting phase plane, we will be able to draw the phase portrait. So what do we see here? One is having x1 equal to 1 by -3. So I'll get here what? Y equal to -3x. That means here negative. So this will be plotted in the other coordinate. And this is what x2 equal to 0 and 1, so I'll get here 0, so this will lie on this plane. Now what do I see? Both these eigenvalues are negative. Both these eigenvalues are negative. That means both of them are exponentially decaying curve, which means both of them, these curves arrow will be converging to origin or 0. So the same will think, these two curves will have an arrow which is converging to 0. So this is my curve. And how will my face portrait look like? Your face portrait will just look like this. It will start here and the other one this is your face portrait. Now since this, in this case, what do we find out? Both of them are moving outwards towards from the origin. Therefore, all the solutions are gone be away from the origin. So, these are unstable node. And since what do we see here is that in both the using both these curves, these face portrait are coming towards the origin. So, it is stable node. So we are already done with the two categories. One is when both the eigenvalues are real positive, when both the eigenvalues are real and negative. Now next category will be what? We are done with both positive, both negative. Next category will be when one is positive and one is negative. So now next case we choose a system. Suppose we have a system number 3 which is considered as 4, 2, 0 and minus 1. Now as we are given with this system matrix, again using the concept lambda I minus a equal to 0 and ax equal to lambda x. Using these concept, I will get lambda 1 equals to 4. With this, x1 state vector will give me 5 and 2. And lambda 2 will be minus 1 with state vector of 0 and 1. So what do we see here? Here we are getting a system matrix, and with using these two concepts, I am finding out an eigenvalue and an eigenvector corresponding to my eigenvalue. So what do I see here? That these two values are real, but one is positive, another one is negative. That means one will have exponentially decaying curve, another one exponentially growing curve. So now with the help of these state vectors, if we again draw a face plane, along with that your respective, these two are phase vectors, phase variables. So this one will give you, x1 will give you what? Y equal to 2 by 5 of x. That will look like this. Another one, x2 equal to 0. So that means it will follow this particular plane. So when I have this expression, it is positive. Positive means what? The arrows will be away. And the one which is having a negative, these will be arrows converging towards my origin. So this is my curve look like. Now how to draw the face portrait? This face portrait will be, your face portrait will start from following this arrow and go out. Same way, it will start from here and go out. Start from here and you can have few more if you want. Same way here and here too. Now this is actually a condition where it is not possible for us to say whether a system is stable or unstable. That's why this particular case, when we have an eigenvalue, one positive and negative, in that case those equilibrium points is termed as saddle point. Next category will be when I use repeated positive eigenvalue. This is my repeated positive eigenvalue. Suppose I consider a system matrix A equals to 2, 1 by 3, minus 3 and 4. So we have here lambda 3, which I obtained by using the concept of lambda I minus a equal to 0. That means in both the situations, by solving this value, both the cases I'll get the same value of lambda, and the vector will be also 3 minus 1. That means we have repeated positive eigenvalue. That means if I draw a phase plane, my equation will look like this. If I use x equal to 3 by 3 and minus 1, these are my state vector obtained by using this eigenvalue. So the equation will look like minus 1 by 3 of x. So this will be in the different coordinate. This is my equation on the negative side. This is what y equal to minus 1 by 3 of x, obviously minus. And since I am getting lambda equal to plus 3, means it's a positive value, which indicates that it will have an exponentially growing curve. So these arrows will be away from the origin. And hence, since I have only one eigenvalue, or rather I should say I have a repeated same eigenvalue, therefore my phase portrait will look like this. It will start from here and it will follow this line. Same for here, it will start from here and it will follow this line. So this is my phase portrait when I have a repeated positive eigenvalue. Next is when I have repeated negative eigenvalue. Now one more thing, since this arrow indicates that these are all moving outwards the origin, system is unstable. Next is when we choose next concept, that is repeated negative eigenvalue. So when I consider repeated negative eigenvalue, we have to first take a system matrix like minus 7, 1, minus 4 and minus 3. This is my system matrix. Now using the same concept of lambda I minus a, you do and find out lambda which is of minus 5 and the state vector will be 1 and 2. Since it's 1 and 2, these two are the eigenvectors for lambda equals to minus 5, equation is 2x. So what happens? Again a positive. So what do I get? I draw again a phase plane. I have 2x. So this is my equation, y equal to 2x. Since I am having a negative, which means an exponentially decaying curve, so I will have an arrow which is towards the origin. So same thing, when this is completed, we have to draw the phase portrait. So our phase portrait starts like this. It will start here and end up here in this place. Same way for this also, it will start from here. It will start from here and end up here. So one arrow will start from this coordinate and end up here, and next one will start from here and end in this coordinate. This is my phase portrait when I have eigenvalue, that is a repeated negative eigenvalue, and with the help of the phase rather eigenvector we have drawn this curve, and then with this value I have drawn the phase portrait for the repeated eigenvalue. And since in this particular case we see that the portraits are towards the origin, therefore system will be stable. Next, for the next case, when I have a complex conjugate eigenvalue. Supposing we have a system matrix with -2, -3, 3 and -2. This is my system matrix given to me, and I am asked to find out the phase portrait. So when I use the concept lambda I minus a equal to 0, I will get lambda as -2 plus minus 3i. Now this falls under the category here, complex eigenvalue when real part is negative. For us, we have a real part negative, so it falls under the category negative. So when we have a negative real parts of a complex conjugate, this particular complex conjugate portion will be indicating that I have a particular cos term as well as a sine term. So because of this cos and sine term, now my trajectory will not look like a straight line. It will be having a curved line. And so since the value of the eigenvalues are in terms of -2, so if I draw a phase plane, first of all this eigenvalue should converge towards origin. And secondly, since I am having minus or rather plus minus of 3i, I have a term cos and sine both present into my respective expression. That means the trajectory will look like a curve or a spiral, and the spiral should go enter inside, or rather it should converge towards the origin. So if I start my trajectory here, it will look like this. So this is the phase portrait when I use, or when I have an eigenvalue with a negative real part and with a complex conjugate part indicating sine and cos time present into my respective expression. This is the case when I consider negative real parts of complex conjugate. Now the next category will be when I have a complex portion of my eigenvalue having real part as a positive value. So same way I will use